Hi, welcome to Cloud-hypervisor, a rising Rust-based virtual machine monitor. I am Michael from ARM. I will start with a brief overview and introduce a little bit about Rust language, the history of Rust-based virtual machine monitors, the architecture of Cloud-hypervisor, how to use it, and what we have done on ARM. In the second half of the session, I will play a demo to show how to build Cloud-hypervisor from source code and how to use it to start a VM. So, what is Cloud-hypervisor? Cloud-hypervisor is an open source virtual machine monitor, or VMM. The project was started by Intel in the middle of 2019. It is implemented on top of Rust-VMM, which is another open source project major in providing software components to build virtual machine monitors. The conventional choice for virtual machine monitor could be based on QEMU. QEMU is powerful but heavy-weighted. It supports many architectures and emulates a lot of devices, including some quite legacy ones. But for a virtual machine running in a cloud computing center, usually it doesn't need to cover all the old devices. Cloud-hypervisor focuses on cloud workloads. It supports only a limited set of parallel-virtualized devices. Cloud-hypervisor is written in Rust language. Rust has been rising in the past few years. Now it is one of the top popular languages. Why is Rust good? Let's compare it with C language. C has some serious pitfalls in memory safety. It uses pointers. Pointer is powerful but dangerous. A C programmer has to be very careful to get rid of all these traps. I believe most C users must have run into segment faults caused by classic null pointer dereferences mistake. This is impossible in Rust. Another error-prone case in C language is in allocating and deallocating memory. If you forgot to free the memory you had allocated from the heap, it would be leaked. But in Rust, no memory can be leaked. Another kind of problem that can be caused by using pointers is so-called dangling pointers, in which case a pointer directs to wrong address in memory. Usually, this kind of problem is very difficult to debug. You will not get this pin in Rust. Buffer overflow is another kind of common memory error in C, which can lead to serious security threats. This can also be avoided in Rust by the nature. To win such a lot of memory safety features, do you need to pay in performance? No. Some languages with similar memory safety mechanism, like Java, is compiled into some intermediate code and got interpreted and executed by some local engine. But Rust is different. The code is compiled into native library, so the performance is the same level with C program. Why is Rust safe? There are some features that make Rust memory safe. They are ownership, borrowing, immutability, and concurrency. I will compare some very simple C and Rust code to illustrate. On the right half of this page, I'm showing two pieces of source code are displayed. The code on top is written in C. In the code, we allocate an integer from heap and pass its pointer to a subroutine named increment, where the integer is increased by 1. Then coming back to the main function, we print the integer. Some risks exist in the C code. A pointer is used. Both main and the increment function can access and modify the memory it points to. What if I deallocated the memory in the subroutine or modified the pointer directing to somewhere else? If I did that, a crash may happen. Another mistake is that I failed to free the heap memory explicitly. Below is the code written in Rust doing the same thing. I used a box to allocate the memory from heap and initialized it to 0. Then we try to increase the integer in increment subroutine and printed the value in main function, just like what we have done in the C code. Is there anything wrong? Yeah. The syntax of the code is correct, but it doesn't build. If you try to build the Rust code, the compiler will give you two errors. The first error reported by the compiler is in increment subroutine. When I try to modify the integer value, the compiler told me that I can't assign because a variable in Rust is immutable by default, except you explicitly specify it as mutable. The concept of immutability can help you avoid unexpected change in memory. Now let's see the second error. The compiler doesn't allow us to access x after passing it to function increment. That is because of ownership. Ownership is the central feature of Rust. In this example, when I passed x to increment subroutine, the ownership of the memory was transferred from the main to increment subroutine. So after that, the memory x doesn't belong to main. That's why we can't access it anymore. The concept of ownership can avoid the memory from being modified here and there, and it also makes safe concurrency possible. All the features of Rust make it a good option for writing low-layer software. Based on these memory safety features, open source communities have been exploring to use Rust in virtualization. One of the achievements is Rust-VMM, and Cloud-hypervisor is built on top of Rust-VMM. Now let me tell the history of it. The story begins from CrosVM. The first well-known virtual machine monitor written in Rust is CrosVM. It was published in April 2017 by Google. CrosVM is based on KVM. It is designed to run untrusted operating system with virtualized devices on Chrome OS. Later, in October the same year, Firecracker project started. It shared some basic concepts with CrosVM. It is also on top of KVM and written in Rust for memory safety. In the very beginning, Firecracker was forked from CrosVM, but it became different soon because Firecracker aimed at different use cases, that is, lightweighted virtual machines or micro VMs. Micro VMs are used for creating multi-tenant containers and microservices. Firecracker has no interest in emulating devices. It only covers the minimum device size it must have. As the two projects have much similarity in functionality and source code, duplicate effort exists in each one's development path. When a feature was added in one project, it could be needed in the other project as well. The code needs to be ported from one to the other, and more effort was used in testing and code review. How can this be improved? In December 2018, developers from Amazon, Google, Intel, and Red Hat discussed the way to share the code, and finally concluded to start Rust-VMM project. Rust-VMM is a collection of crates designed for making virtual machine monitors. A crate is a building block in Rust, like a library in C. It provides common used data structure and interfaces. To create a VMM, you only write the minimum and custom code to connect these crates. Today, almost 20 such crates have been created. All of them haven't been finished. Many of them were still under developing, but the most basic ones have been ready. In a later slide, I will introduce some of them. In May 2019, Intel announced a new VMM project, that is, Cloud-hypervisor. It was based on Rust-VMM. Here is a diagram to show the major components of Cloud-hypervisor. Let me introduce them from bottom up and left to right, one by one. On top of host Linux kernel, it is Rust-VMM. It contains many basic crates for building a virtual machine monitor. KVM bindings is a Rust language binding of KVM data types in kernel. KVM IO controls wraps the IO controls to KVM into Rust interface. There are also other crates for loading guest kernel, managing guest memory, and handling events, etc. On top of Rust-VMM, it is Cloud-hypervisor. Currently, Cloud-hypervisor is based on KVM, but KVM will not be the only choice in future. From the second half of this year, Microsoft joined the community and began to extend Cloud-hypervisor to Hyper-V. The work is still ongoing. A new crate was designed to wrap low-layer hypervisor details. That is the hypervisor crate. It has the details of KVM and provides unique interface to upper-layer components. Architecture-specific things are placed in Arc crate. For ARM64, we have code handling, gig, and FDT here. VMM is the core component of Cloud-hypervisor. I have mentioned that on top of Rust-VMM, an active virtual machine monitor should only contain customizing code. In Cloud-hypervisor, the major customizing part is VMM crate. It manages devices, memory, CPUs, and interrupts of the guest. VMM create also maintains the lifecycle of a guest. It opens an API server to take requests. Users can control Cloud-hypervisor through a REST API to boot a guest, shut it down, suspend, resume, and so on. VM allocator is a resource management component. It is in charge of allocating and deallocating RAM addresses, I/O addresses, and IRQ numbers of a guest VM. The last part is devices. It contains some crates for VirtIO and the host user devices. Ideally, the VirtIO stuff should be designed agnostic to any concrete VMM implementation. The vision is to make it unique in Rust-VMM, but now Rust-VMM haven't been ready in this part. In future, VirtIO things in Cloud-hypervisor should be replaced by aligned Rust-VMM components. This page lists the devices supported by Cloud-hypervisor when this slide was written. On x86, they are serial port, CMOS, IOAPIC, i8042, ACPI, and every kinds of VirtIO devices, and several kinds of vhost user devices like vhost user block, FS, and NIT, and VFIO. On ARM64, most of them are supported as well, except ACPI and VFIO ones. Here, I will show an example on how to use Cloud-hypervisor to start a VM. I will demonstrate the same example in a later video, including how to set up environment and build some source code. Here, I just explain the command to give you some impression about how Cloud-hypervisor works. Target/debug/Cloud-hypervisor is the VMM binary. With kernel parameter, I specified the guest kernel image or the binary of firmware, but currently firmware is only available on x86. With disk parameter, I specified disk images. Here I used an Ubuntu cloud image and a customized cloud init image, which includes my user account data, and I specified the command line parameters to kernel. 4 vCPUs will be activated on boot, and 512 megabytes memory is assigned. And I configured the network, specified type, MAC address, IP address, and subnet mask. At the bottom is the screenshot of a started VM. You will see it later. With this slide, I will introduce what have been done on ARM and what will be done in the future. To enable ARM in Cloud-hypervisor, we added things like FDT and the Geek. So far, we have supported Geek v2, v3, and ITS. We also enabled MMIO and PCI for VirtIO devices. All these works were accompanied by a large scale of code refactoring. This is the most challenging part. The core part of Cloud-hypervisor was originally designed for x86, so we have to make a lot of change to let the code work on both x86 and ARM. For ARM, there are still some gaps to fill. The closest plan is to support migration, so a user can make a snapshot of a guest VM and restore to it. And in longer view, we have works to do in VFIO, UEFI, the firmware, ACPI, and after that, we will be able to enable features like device hot plug, etc. Next, I will switch to a demo of building and using Cloud-hypervisor on ARM server. Thank you everybody for watching this presentation and the video. Is there any question I can help to answer? Hi. In this demo, I will show how to build Cloud-hypervisor from source code and run a virtual machine using Ubuntu Cloud Image. Everything will be done on an ARM server. The operating system here is Ubuntu 18. If you want to try Cloud-hypervisor on ARM as well, a Raspberry Pi 4B is an easy option. It has 64-bit Cortex-A CPUs and up to 8 GB memory. That's enough for running a small VM. Before this demo, I have installed some basic development tool packages like Git and Build Essential. On ARM64, Cloud-hypervisor requires an additional package than that on x86, that is libfdt. It is used for building the device tree. Now let's make sure it is installed. No problem. It was there. Cloud-hypervisor was written in Rust language. At first you need to install Rust app. It is a command line tool for Rust. It also includes Cargo, the building system, and the package manager for Rust. We just select the default option. You can install the latest stable version of Rust app with one command just like this. Now all the tools are ready. Let's proceed to build the source code. At first, let's clone the source code from Cloud-hypervisor GitHub repository. There isn't too much source code, so it only takes a while to clone all the code. When the source code is ready, let's build the code with cargo command. While the command is executing, let me explain what is happening. Cloud-hypervisor has some features like PCI and ACPI. They are enabled by default, but all the features haven't been ready on ARM yet, so I use no default features to turn off all the features at first, and immediately I use features option to select the features we want on ARM. In this case, they are KVM and PCI. KVM specifies the hypervisor you are on top of. We are using KVM, and now this is the only option for hypervisor. PCI specifies the transport option of VirtIO devices. You can choose between PCI and MMIO. PCI requires the interrupt controller of your host machine to be geek
v3 ITS. If you are on a Raspberry Pi 4, the interrupt controller is Geek v2. You need to modify this IO. The building takes a while. It will download and build the Rust packages in dependency, including Rust-VMM crates. Now it's almost done. Let's wait for a short while. When the building finished, the binary was placed at target debug folder. The binary Cloud-hypervisor is what we need to use in the next step. Now, let me switch to another folder containing the disk images. Here we have a cloud image of Ubuntu and a cloud init disk, which includes my user account data and the kernel binary. Now let's start the VM. I should have introduced the meaning of all the parameters in the presentation, so I will not explain more. Let's just let the command go. Now the VM is launching. Let me log in. Now I can look around the system. Let's have a look at the devices in the system by ls PCI command. Now we have 6 PCI devices emulated. The first one is the host bridge. Besides that, we have a VirtIO console, 2 VirtIO block devices for the 2 disks we have assigned to the VM, and a VirtIO network device for the Ethernet controller, and a VirtIO random number generator, which was assigned by default. Then enjoy the VM. That's all of the demo. Thank you for watching.